All right, let's get into it. Today we are pulling back the curtain on some serious engineering magic, the secret behind that instant snappy response you feel in high-tech machines. We're going to find out why, when it comes to performance, controlling electric current is everything.
I mean, think about it for a second. You know that incredible kick when you stomp on the accelerator in an EV? That feeling of being glued to your seat? Or how a giant industrial robot can move with such surgical precision? Well, that's not just a big motor doing its thing. It's a really, really smart control strategy at work.
Yep, the secret sauce for that amazing performance isn't just about the physical hardware. It's all in the brain. The sophisticated software that's telling the motor exactly what to do down to the tiniest fraction of a second.
So to really appreciate how amazing the new way is, we've got to take a quick look back at how things used to be done. Let's talk about the traditional method of motor control and why it just can't hang in the modern world.
For decades, really, the go-to method was a pretty simple idea called volts per hertz. The logic was easy enough. You want to make the motor spin faster? Just crank up the voltage and the frequency you're feeding it, keeping the ratio between them the same. It works, for sure, but it's got a huge weakness when you need speed and precision. And this quote from the Power Electronics Handbook just nails the problem. The key word here, sluggish. And why is it sluggish? Well, because when you mess with voltage and frequency, you're not just controlling one thing. You're indirectly nudging both the motor's torque, that's its turning force, and its magnetic flux at the same time. You can't really control one without messing up the other.
So you can see the mismatch, right? We're chasing after something instantaneous, direct, and incredibly precise. But the old way? It gives us sluggish, indirect, and imprecise. It's kind of like trying to paint a masterpiece with a paint roller, when what you really need is a fine point brush.
And this brings us right to the heart of the challenge. The entire quest for high-performance motor control, really, it all boils down to one thing: getting total, absolute, instantaneous control over torque. So let's be clear. What is torque? It's just the rotational force, the twist, the grunt work. It's the thing that actually moves a car down the road or swings a robot's arm. If you can control torque perfectly, you can control movement perfectly. Simple as that.
Now, to make that torque, you need its partner in crime, flux. You can think of flux as the invisible magnetic field inside the motor. It's the environment that has to be just right for the electrical forces to create torque. You have to manage it, but it's not the thing that creates the direct movement.
And here we are again, back at the villain of our story. With the old volt/hertz method, torque and flux are basically tangled up in a knot. They're coupled. When you change the voltage, you change both of them. And that's exactly why it feels so sluggish. You can't just command a quick burst of torque because a change in the flux is always tagging along, slowing everything down and making the response all muddy.
But then came the breakthrough. And this quote from the textbook Power Electronics spells it out. To get that crisp, dynamic response, engineers figured out they needed something called an internal current loop. And why? Because it turns out there's a beautifully direct, predictable link between the electric current you send into a motor and the torque it spits out. This was the big aha moment.
So just like that, the entire game changed. The answer wasn't about getting better at juggling voltage and frequency. It was about changing the target altogether. The modern solution is to go straight for the source and control the current directly. And this brings us to the modern-day heroes of motor control, sophisticated strategies like vector control, which you might also hear called field-oriented control, and direct torque control, or DT. They're a little different in how they work, but they are both built on the exact same powerful principle. Current is the most direct lever you can pull to get the torque you want.
Now, this is a really key point. You might be thinking, wait, is this system still using voltage? And the answer is yes, absolutely. The motor drive is still zapping the motor with voltage thousands of times a second. But, and this is the huge difference, the voltage isn't the goal anymore. It's just a tool used to sculpt the perfect current waveform. The real target is always the current, because current equals torque.
Okay, so here's a simplified diagram of how a direct torque control system pulls this off. You've got your commands for torque and flux going in. The controller is constantly looking at what the motor is actually doing, and it's comparing that to what you've asked for. The instant it sees a difference, any error at all, it instantly picks the perfect voltage switch to fix it. It's just a crazy fast, non-stop feedback loop.
And this whole thing is really just a super fast three-step dance that repeats thousands and thousands of times every second. Step 1, measure what the motor's really doing.
Step 2, compare that to what you want it to be doing, when you hit the accelerator. And Step 3, instantly apply the precise little voltage kick needed to force the current and therefore the torque to match your command perfectly.
So we've gone from a sluggish, indirect system to this lightning-fast, direct one. What's the payoff in the real world? What do we actually get from all this complex control?
Well, the benefits are huge. First, you get what feels like totally instantaneous torque control. You want it? It's there. The system is also incredibly robust. It keeps performing perfectly, even as the motor heats up and its physical properties change a bit. And this is a big one. It's safer. By directly controlling the current, the drive automatically stops things from getting out of hand, preventing huge, damaging current spikes when you start up or if something goes wrong.
And that right there connects everything back to the beginning. That instant control is what gives you that snap-your-head-back acceleration. That robustness and precision is what gives an industrial robot its unbelievable accuracy. Pretty much every advantage we love about modern electric drives comes right back to this one idea. Control the current, and you control the machine.
It's kind of amazing to think about, isn't it? We now have a level of precise, instant control over physical force that would have seemed like science fiction not that long ago. So the big question is, now that we can command torque so perfectly, what incredible new technologies and new possibilities is this going to unlock for us in the future? Something to think about. Thanks for tuning in.